How y'all doing? Everybody survive the week, I guess?
Pretty much.
Yeah, good. I'm sure that everybody has stories about how exciting their week was. But we're here, I guess. We all appreciate electricity and water a little bit more, I guess, today. We'll just wait another minute or so for more people to get here. All right, it's 1:01, so I guess we'll get started. So, you know, I'm teaching a couple of different classes this semester, pre-Cal, Cal 1, Cal 2, and then the Cal 3. And I can say I think I'm most concerned about the Cal 2 and 3. The week we just lost is going to be very hard to make up. There's not many places that we can say, oh, we'll just kind of skip that. So normally I always tell my Cal 3 students, like, we're going to finish the textbook, because remember, this class is based on an actual book. So normally I say, oh, we're going to finish the book. I'm going to do my best, but like I said, it's going to be hard. So we're just going to go as far as we can go. And anything that we don't cover, just, you know, understand that I do have videos out there of me covering that material. If you want to watch that on your own, you can do that. Especially this last section, divergence theorem, Stokes' theorem, those are used quite a bit later on. So you want to see those. I'm gonna do my best to get to them. So I guess first step to that is for me to just shut up and get down to business. We do have spring break coming up, and that's going to be, so we have this week and next week, then we have another week off. And so we're supposed to have a midterm, and that's going to be a take-home midterm. And that's a test everyone has to take. It's not like the mini exams where you get to pick. So I'm thinking I want to give that to you on the Wednesday. This is all messed up. I didn't realize that was messed up, but the Wednesday before spring break, I'll give you the take-home exam, and then I'll probably make it due like after spring break, the week after, because I don't expect that you're going to sit there and do work over spring break. It is officially a break. So, but I know that you'll have time, and so you can use that time to do the test. So anyways, let's just see where we can get here today. We're supposed to be starting limits and continuity, and we are still in vector functions and space curves. All right, so let's get down to it. So we left off, and I think it would be unfair for me to not do a quick summary of what we had done. We had started talking about vector functions and space curves, talked about, you know, we can have two or three dimensional curves that these are vector valued functions like this draw curves. That was the important thing, all right, that it draws curves in either 2 or 3 dimensional space. And we looked at those. We looked at a couple of examples in 2 or 3 dimensional space. Then we started talking about the limits of a vector function. We said, oh, it's just the same as Cal 1, except you just take the limit of each of the component functions. And then on the mini exam, there were some limits on there that you got to work with if you did the mini exam. And then continuity, we talked about continuity. And then we talked about derivatives and how if you want to take derivative of a vector function, you just take derivative of each of the components. So that was pretty straightforward. Then we talked about the geometrical meaning of the derivative and how when you take the derivative of a vector function, it always gives you a vector that is tangent to the curve at that particular point. And then we talked about the unit tangent vector, which is basically the tangent vector scaled down or scaled up to have a length of 1. And then we talked about second derivative. Then we talked about smoothness. And then I gave you all these differentiation rules for taking derivatives of vector valued functions and how when you get to dot product and cross products and taking derivatives, it looks a lot like the product rule from Cal 1. And then that's where we stopped. Okay, so we had stopped right here. So our first example picking up from last time is this one here, is to show that if you have the vector function r of t equals cosine t sine t, that r of t is orthogonal to r prime of t for all t. All right, so let's work that out. So I know I stressed this to you, the whole idea of cosine t sine t and how that draws the unit circle, right? And if you put a number in front of these, then that would draw a circle with a different radius. So if this were like 2 cosine t, 2 sine t, then you'd have a circle radius 2. So this is saying that if we have a two-dimensional vector function, so a curve in two-dimensional space, and in this particular case, the unit circle, right? This is r of t, that we're supposed to show that r of t is orthogonal to its derivative for all t. So I think you can see this geometrically. We're saying that if you take a vector that gives you a point on the circle, that would be r of t at some particular value of t, that the tangent vector, r prime of t, must be orthogonal to r of t. So this must be a 90-degree angle. So can somebody tell me how we could show that that's true? And what it would mean for those to be orthogonal?
If you take the dot product of them and it'll be 0.
Yeah, so we just want to show, WTS, we want to show that when you take r of t and dot it with its derivative, you get 0. Okay, if we can show that, then we know that they are orthogonal vectors. All right, so let's do that. Well, r of t is just given to us. It's cosine t sine t. And we're going to dot that with its derivative. Now, when you take the derivative of a vector function, you just take the derivative of each of the component functions individually. We know the derivative of cosine of t is negative sine t. And we know that the derivative of sine t is cosine t. So there's your derivative. And now we dot them. And dotting, remember, if you take two vectors and dot them, you get a scalar. So I'm going to take these two, multiply those together. That gives me negative cosine t sine t. And then I add to that the other two components multiplied. So that's sine t, cosine t. And it's obvious that those are opposites. So that will add up to be 0. And we're done, right? We've shown what we need to show. That's very straightforward because they gave us a vector function. We could calculate what its derivative was. We could dot them and we could show it's 0. Now, I'd like to compare that problem to the next one, which is a lot different. Oh, this is just a picture of what we just did. We just showed that no matter where you are, the derivative is orthogonal. So take a look at this one. And I was debating how I wanted to go about this problem. I thought about putting you all into breakout rooms and stuff and letting you talk about it and think about it. And then I realized we're a week behind. So we're not going to do that. But let's just try and understand the question first. Show that if the magnitude of a vector function is constant, okay? So that means that the length of the vectors, when you're drawing a curve, right? And the length of each of those vectors is always constant. Now that could be a 2-dimensional curve or it could be a 3-dimensional curve. It doesn't matter. In fact, it could be any dimension, but if that's a constant, then show that R of t is orthogonal to R prime of t for all t. So again, we want to show that when you take R of t and dot it with its derivative, you get 0, right? That's what we would need to show. But what's the problem? I mean, what's different here? Why can't we do it the way we just did the problem before?
They don't actually give us a vector.
Yeah, we don't know what the vector function is, right? They're saying the only condition, the only thing that they're giving us is that when you take the magnitude of the vector function, you get a constant. Now, let's try and wrap our heads around what this means geometrically. The way in 2-dimensional space, here's what it would look like. In 2D, it would look like this. You're drawing a curve, right? You have to draw a curve, but the length of every vector you draw has to be the same length for all the vectors. So it could be a circle, right? That would qualify. But it could also be something that does this. Just watch my orange drawing here. I could start drawing, and then I could come backwards and draw this way and kind of loop back and go back. As long as I'm drawing, I'm constantly on that circle, right? Like as long as I'm on that circle, then every vector has a length of c being this distance here. So it could be a circle, but it could also be, think of it as like a little ant walking along the edge of this circle. The ant can go forward and then move backwards. It doesn't have to travel in a circle continuously. It can stop and reverse direction and things like that. So, but I think as long as we're in a circle, I think that we could all agree that a tangent vector would be orthogonal, right? How about in 3-dimensional space? What would this be like? All vectors have to have the same length. It would be like, yeah, it'd be like an ant crawling along a sphere, right? So you have this like 3-dimensional sphere and you've got some ant on the sphere and the ant is crawling around doing whatever it wants to do. So that's a curve in 3-dimensional space, going around the back side of the sphere, walking around, whatever. And what we're trying to show here is that no matter where you are on that red path, the tangent vector will be orthogonal to the original vector function. So if you look at like a vector from the center out to one of the points, that your tangent vector should be orthogonal. So maybe it makes sense geometrically, but that doesn't help us prove it. So I don't know if there are any people out there, any of you are math majors or not, but do I have any math majors here? I think I have at least one. No? Yeah, math. Okay, so this is a really good example of the type of problems that math majors have to do, okay? Because there doesn't seem to be anything to work with here because we don't have a vector function to take the derivative of and dot and get 0, right? So we have to somehow get to this, and I'm going to show you how to do it. And when you see it, you'll be like, well, I'm not quite sure I would have ever thought of that, you know? And that's just kind of the nature of the way mathematicians have to start thinking a certain way. So here's what I'm going to do. I'm going to look at this and I'm going to say, well, what was I given, right? This right here is the biggest piece of information that I'm given in this, right? That the magnitude of the vector function has to be a constant. And I somehow need to show that equals that when you dot that, you get 0. All right, so what is something I know about the magnitude of a vector? Let me go back to when we were learning about vectors. Does anyone know a relationship that we might be able to get between the magnitude of a vector and the dot product of something? We do have a property that connects dot products and magnitudes together.
Is it the equation with the cosine theta.
We do have that one. Okay, so I'll write that down just because it is something we have. We know that if we take two vectors and dot them, it's the magnitude of u times the magnitude of v times cosine of the angle between them. We do have that one, right? And this was if we had two different vectors and we dotted them, then we have the magnitude of each, right? Times cosine of the angle between them. Okay, let's work with that. In this case, we only know the magnitude of r of t, right? That's all we know. So here, see, in this formula, we have two different vectors, right? U and v. So I'm not quite sure how we could use this. I mean, I know we can, I know how we can, but I'm trying to get you to stumble upon it. Are there any other relationships we have between dot products and magnitudes?
I can't remember what it was called, but was it that projection?
Okay, so we have projection
Or
that had magnitude and dot product in it, give us the length of some other vector when you projected it. It gave us the vector and then we could find the component or the projection. Yeah, that's something that connects the two. There's a very simple.
Yeah, I saw one in the textbook. It was written as a dot b equals the magnitude of a squared.
Okay, that's the one. You didn't say it right, but you're on. That's the one. Okay, so look, we have this. If you take u and dot it with itself, okay. If you take u dot u, let's see what it would be using that formula that we were just talking about. This should be the magnitude of u times the magnitude of u. Okay, so what is the angle between the vector u and itself?
0.
0, right? So what's cosine of 0?
1.
1. So this is the magnitude of u squared, isn't it? So do we all agree with that? Cosine of 0 is 1. So does everyone understand? If you're dotting a vector with itself, then they're pointed exactly in the same direction, so the angle between them is 0, right? Okay, so look at that relationship we have. U dotted with u is equal to the magnitude of u squared. So if we rewrite that as the r vector, right? That's a vector. R of t is a vector. And we dot that with itself, r of t, then we know that that's the magnitude of r of t squared, isn't it? And that we actually know the magnitude of r of t. What's the magnitude of r of t? Some constant, right? So I could now still, I don't know where the hell I'm going to go with this. I'm just trying to figure out some relationship that I can work with, right? This may be a dead end, it may not, but I've got to do something, right? Okay, so do y'all agree with that? If the magnitude of r of t is c, then c squared, then that's true, right? For this particular problem, this is true. How am I going to get from that to that? Because this is r dotted with itself, not with its derivative. So any ideas? We're missing a derivative, aren't we? We don't have a derivative in here?
can we just get that derivative?
Okay, so how? Yes, but how?
Would you derive the c squared and use that as your derivative constant?
Yes, let me go back. Let me give you, look at this here. Which one of those should I be looking at?
Number 4.
Number 4. So how do you take the derivative of two vector functions being dotted together? Well, you take the derivative of one of them and dot it with the other one, then plus the derivative of the other one dotted with the original one. So this is like product rule from Cal 1, isn't it? So, I mean, can I do that? If I have an equation, right? I have an equation here. Can I just differentiate both sides of the equation? Sure, why not, right? Let's take the derivative with respect to t on both sides. So if I take the derivative with respect to t on the left, something is going to happen. We'll do that in a second. And then if I take the derivative with respect to t on the right, well, that's good. Because what's the derivative? Well, constant squared is still a constant, right? And the derivative of any constant is what?
0.
0. Okay, so the right-hand side of this is 0. And I'm already starting to get happy because I'm supposed to show that something is equal to 0, and I'm actually getting a 0 here somewhere. And then here, I'm just going to do like the product rule. This is going to be the derivative of the first one dotted with the second one, plus the derivative of the second one, which is still the same thing, r prime of t, dotted with r of t. Understand? That's just like a product rule there. Now, do you all agree these are the exact same thing? Yes. So I actually have 2 of those. I have 2 of these r of t dotted with r prime of t. That must be 0. And because 2 is a scalar, I can just divide both sides by 2. Right? If I divide by 2 here and divide by 2 here, it goes away, and the right-hand side is still 0. And what I have is r of t dotted with its derivative is 0, which is what I wanted to show. Right? That's weird, right? Like where would you ever have like come up with that? So you see, this is the way math majors have to start thinking. Is, you look at the problem, you say, okay, look, what am I trying to show? What am I given? And how can I somehow use this given information to arrive at this conclusion? And you just start putting things down, and you have to just start trying things. I don't think anyone in here would have naturally said, oh, we just, oh, go to that property, you know what I'm saying? So you train your brain to start thinking a certain way. There's not going to be any problems like this where I test you like this on things like this, because something like that this is more of like a show, like expose you to this so you can have an appreciation for how we can arrive at things that don't look like we could ever arrive at them.
I thought it was going to be a lot harder.
Yeah, well, the hard part is knowing what to use, right? Knowing to use this, and then knowing once you get here to differentiate. Those are the key parts. Okay. The good news is, just like, in every level of math, once you see it, things aren't hard, right? Once you see it, it's that gray area we all get lost in math, right? That's when it sucks. Okay, so applications of derivatives. So this is a really important concept, all right? Because this is where we start to differentiate, and I don't mean differentiate in the sense of calculus take derivative. This is where we begin to separate the idea between a vector function and just a curve that we did in like college algebra pre-calc cal 1. Right, there's a difference between the two ideas. So when I first made these notes, I took these really, really like slow baby steps to go through this. I'm going to go a little faster here. I'm defining 2 vector functions, okay? Little r1 of t and little r2 of t. So these are 2 different vector functions. The first one is t squared. Those are the 2 component functions. The other one is t squared and t to the 4th. And we're going to be plugging in values of t that are greater than or equal to 0. So if you look right now and check, if you plug 1 into this first one, you get 1 squared, which is just 1, 1. And if you plug 1 into the second one, you also get 1, 1. Now, if you plug 4 into the first one, you'll get 4, 16. And if you plug 2 into the second one, you'll get 4, 16. And it turns out if you graph these, okay, if you graph them, they draw the same curve, right? They would draw the same exact thing. However, there is a major difference between the 2. And that's why we, like what I'm trying to say is in algebra or pre-cal or calculus, you look at those 2 curves and everyone says, oh yeah, they're identical. But in terms of vector functions, just the drawing itself is not enough to say that if we're comparing 2 things, it's not enough to say they're equivalent. So what I'm going to do is I'm going to start a clock here. And I'm going to let the computer plug in t and just watch the dot move and just notice what happens here. So they're both drawing the same curve, but I think it's clear that the one on the right is the dot is moving much faster across the curve, right? And that's critically important because remember that the derivative of a vector function is a vector that is tangent to the curve, right? And so the next natural question would be, are the tangent vectors going to be the same, right? Are they the same? So I'm going to show you the derivatives. So here are the derivatives. Here's the derivative, the tangent vector for this one in black and this one in purple. Now, notice they're not at the same point. It's the same point in time, but they're at different places on the curve. What would be interesting for us to look at is if we're at the same point on the curves, like, you know, if I'm here on this one and I'm at the same place here, do you think that their tangent vectors would be the same? What do you think?
No, I don't think so.
Yeah, it's not going to be. And it's because the tangent vector represents the velocity of the point that's moving, okay? So if we're drawing the one on the right faster than we're drawing the one on the left, then the tangent vectors should be different. So here's a look at the vectors. I've just picked a few for us to compare here. Let me get this out of here. Okay. Let me get that out of there completely. Okay. So yeah, it's hard to see this, but these correspond to the same points in time. So here and here are the same points in time, and then here and here are the same points in time. And you can see that this tangent vector, this black one, it is pointed in the same direction as the purple one. Okay, so they have the same direction, but they don't have the same magnitudes. And so they are different vectors. All right. So that's the big thing to take away from this, is that even though you have two vector functions drawing the same curve, it matters. It matters how fast that point's moving. That's going to be a unique characteristic of each of these is that tangent vector. All right. Okay. Any questions on that? All right. So some definitions here. If our vector function r of t represents the path of a particle or an object moving through space, then we call it a position function. So this is something in college, or sorry, in Cal 1, you do learn about position functions. But if you remember, if you go back and look at your Cal 1, when you're talking about position functions, it was always straight lines. Everything had to be traveling in straight lines. Here, we don't have that restriction anymore. We just have an object moving through space, all right? Doesn't have to be a straight line. Then v of t, which we will define as the derivative of r of t, is called the velocity function. So you start with the position function, r of t, you take its derivative and you get the velocity function. Now, if you look at the magnitude of that derivative, so the magnitude of the velocity is called the speed of the particle at some point in time. So when you're in, I know when I'm in Cal 1, I always ask my students, is there a difference between speed and velocity, right? And most students in Cal 1 haven't taken physics or something, so they don't know, but there is a difference, right, between velocity and speed. Velocity is a vector. It's a direction and a length. Now, that length is the speed. So velocity is direction and speed together, right? The speed is just the length of that vector. That's all it is, all right? Now, the acceleration is just the derivative of the velocity function, of course, is called the acceleration function, all right? The larger the magnitude of the derivative, first derivative, the faster the particle is moving at that point in time. All right, so there's some homework problems, but now what we're gonna do, we're pretty much done with the basic idea of differentiation. Now we're gonna talk about integration. So if you start with the vector function r of t, whether it have 2 components or 3, it doesn't matter what dimension you're in here, then if you want to do the integral of that vector function with respect to t, then the good news is you just integrate each vector function individually. So this is the same thing as differentiation. You do it component by component. All right. Now, the important thing is that your answer is a vector. Okay, so when you do this antiderivative here, you're going to get something here, some function or a number. And then here you're going to get a number, and here you can get a number, but they're all in the angle bracket, so you wind up with a vector. All right, so here's an example. It's asking us to find the integral from 1 to e of r of t dt. So all we have to do here is take that vector function and take the antiderivative of each of the component functions. So let's just do these one by one. I'll start with the e to the t. So we integrate e to the t with respect to t. And we're going to go from 1 to e, right? That's what we're doing. Now, to do this, I think this is a straightforward antiderivative. Would you all agree? Right? The antiderivative of that should just be itself. And then we are going to evaluate that from 1 to e, right? So in Cal 2, what we did normally is we just put like, this was called the evaluation bar. We put a 1 here, we put an e here, right? Like that. Now we can do that, all right? There's nothing wrong with that. But because of where we're headed, I'm gonna do it a little different, because you'll see later, we're gonna wanna know what variable we're talking about. So I'm going to say t is 1 and t is e. I mean, there is only one variable here right now. So when we put 1 and e here, we know we're talking about t. But later on, we're gonna have 2 variables or 3 variables, and we need to know which one we're actually plugging in and replacing. In this case, we're replacing t with e, and then t with 1, and we're subtracting. So this is your fundamental theorem of calculus, the evaluation theorem, right? This is just e to the e minus e to the 1. We just plug in. And that's, we'll just leave it like that. That's what it is. That's a number. I'm not going to get a decimal, just going to leave it like that. So my answer so far is e to the e minus e, comma. Now I need the second component function. So now what I need to do is do the integral from 1 to e of t square root of t minus 1 dt. And do y'all remember in the beginning of the semester, I said, this class is really about, there's like no new math here in terms of like differentiation, integration. It's all differentiation, integration. We have new definitions, new ideas, but there's no like new big math thing. But that means that as you do these problems, like on the mini exams, you're doing limits. You're having to go back and like dig up stuff from the past. Okay, that's the way it should feel to you, is like, oh man, it's been so long since I've done that. It should feel like you're digging things up. Now this is Cal 2, so this is more recent. So anyone have an idea of how we would integrate that?
Put the t out in front of the.
What do you mean?
So pull out the t. Is that a constant?
Out here? No, t's not.
Yeah.
T's not a constant, because this is with respect to t. So t cannot come out.
I wish I know what it is. I can't remember the name of it though.
Is it
Okay.
integration by parts?
That one.
You could try integration by parts. Let's do this. Let's do an indefinite integral first, which means let's not worry about the limits of integration. Let's just do an indefinite integral and see if we can find the antiderivative. Now, integration by parts could work. I'm pretty sure it would work, but I think there's an easier way.
Would it be u substitution?
Okay, if you did u sub, what would you use for your u sub?
It would probably have to be t minus 1.
Okay, let's try that. U is t minus 1. All right, now look, this is where everyone kind of had a different experience in Cal 2, all right? Depending on your professor, there's slight little differences in notation and the way you did things. And I realized that's present here. So if I do anything that's like, what the hell, just let me know, okay? If it looks completely different than anything you've seen, I'm just writing it. This is basically u sub. That's the technique I'm using of integration here. I'm going to take the derivative on the left with respect to t, and I'm going to take derivative on the right with respect to t, which is just 1. And then I'm going to write du, I'm going to basically multiply both sides by dt, so 1 dt. So that's where I am. This is a substitution problem. I'm going to replace the t minus 1, I'm going to replace that with u. And then I need to somehow replace the dt with something. So I'm going to replace the dt with du, because that's what dt is, right? dt is equal to du. The only thing I don't have yet is what I'm going to replace the t with. So how do I do that?
Add or subtract 1.
Yeah, take this equation here and let's get t by itself. So I'm going to add 1 to both sides. So now I know that I can replace t with u plus 1. So the whole idea behind substitution is to make a substitution that turns your integral from being in terms of one variable over to a different variable. So we're going here from t to u. And by doing this, let's see what the new integral looks like. Let me do the square root part first. The square root of the blue stuff is just square root of u. And then the green, the t part is now u plus 1. And then the dt is just du. So I've got that instead. And what's good about this one is that I can distribute the square root of u through. And that becomes, I'll just use rational exponents now. This becomes u to the 3/2 plus u to the 1/2 du. So I'm just rewriting, square root of u is just u to the 1/2, and then I multiply here, I add 1/2 plus 1, I get 3/2, and then this times 1 is itself. And now I can just integrate these term by term, right? Just one at a time. So the antiderivative of u to the 3/2 is
3u something, I forgot.
we have to add 1, right? Because we're doing antiderivative. So we add 1 to the exponent, 3/2 plus 1 is 5/2.
So it's 2/5 u to the 5/2.
2/5 u to the 5/2 plus, same thing, add 1 to that, so 3/2, so 2/3 u to the 3/2. And then we would have plus a constant, right? Since we're doing an indefinite integral here. Is that clear to everyone? Now I'm going to replace u with t minus 1. There we go. So that is the antiderivative. Now what I'm going to do is I'm going to go back up here, right here. And I'm going to say that that is equal to that antiderivative evaluated from t equals, what was it, 1 to e, right? So first I plug in e, right, for all my t's. So this is going to be 2/5 e minus 1 to the 5/2 plus 2/3 e minus 1 to the 3/2. Okay, so that's me plugging in e, and then I'm subtracting from that what I get when I plug in 1. But that's good because when I plug in 1, I get what, 0 here and 0 there. So everything just goes away. So I just get 0, so there's nothing there. So that should be my second component. So that's going to go here, 2/5 e minus 1 to the 5/2 plus 2/3 e minus 1 to the 3/2. Comma. Okay, I need my last one now. So this isn't, I mean, there's, in terms of the Cal 3, there's nothing new here except that we're finding the antiderivative of a vector function, right? That's it. The mechanics for this is just Cal 2. So my last one is natural log of t. I'll do that in red. Integral natural log t dt, going from 1 to e. All right. So on this one, this depends. I know in my Cal 2 class, we actually go and derive what this is, and then I let my students put it on their formula sheet. But in this case, let's act like you don't know it. So anyone know how we can find the antiderivative of that?
Isn't it just 1 over t?
That's the derivative,
Okay.
right? So we're looking for the antiderivative.
I don't remember I don't remember it, but I remember sort of it. So in case it rings a bell, I think it was like something times the natural log minus the natural log of something.
Yeah,
There's something around there.
yeah, I can remember being in like your place around Cal 2, 3, and that's the way I remembered it too. It's like I wasn't quite sure, but I knew it had natural log something minus something or something like that, right? So we're going to use integration by parts here. Integration by parts. Now again, this is always going to be different depending on your experience with this. All right. So I'm going to present this the way I teach my class. So what I'm going to do is I'm going to use the formula that when you do integration by parts, you have this formula u times v minus the integral of v du. Now, how many of y'all learned that ultraviolet minus voodoo? A lot of you learned that ultraviolet minus voodoo. Terrence, yes, no?
Mine was Uvalde minus voodoo.
Okay,
I just had to remember that.
you just remembered it. Okay, so ultraviolet minus VOODOO. Is that right, voodoo? I don't know. Someone came up with that, not me, but it's just a way of remembering this. Ultraviolet minus, now you have to remember the integral sign. VDU is voodoo. It's just a little cute way of trying to remember the formula. So the whole idea behind, and I wish if this were Cal 2, I'd get into this in more depth. The whole idea here is that we have two things here being multiplied. We have to let one of these be u and the other one be dv. Sorry, other way around. We have to let one of these be v. No, I said that right. U and then dv. And then we have to use that and then use this formula. But you don't have to do it that way. You could do it the other way around. You could have this be the dv and this be the u. Again, I'm not going to get into a whole long thing about integration by parts. So the way I tell my students or show them is, and this is the way I do integration by parts, is I draw a table. And here I put u, and down here in this corner I put dv. And what I have to do now is use that integral and assign. I get to choose what's going to be u and what's going to be dv. So I'm going to go with u being natural log of t, and dv is going to be the only other thing that's up there, which is dt. And then the way the table works is that when you go down, you have to differentiate. So when I take u, I take its derivative, I get 1 over t dt. And when I go from dv up to figure out what v is, I have to integrate. So I'm taking the antiderivative of 1 dt, which just gives me t. And now once I have the table filled out, I just use this formula. So this integral becomes ultraviolet, which is this times this, which I'll write t times natural log t, minus the integral, and now voodoo is going to be these two multiplied together. So that'll be the t up top, that's v, and then du is 1 over t dt. And those t's cancel out. So you get t natural log t minus just integral of 1 dt. And the antiderivative of 1 is just t. And then plus a constant. And now that's our antiderivative. Now we need to evaluate it. So I'm going to come back up here. This will be equal to t natural log t minus t evaluated from t equals 1 to t equals e. All right, plug in. So if I plug in E for t, I get E times, what is natural log of E?
1.
1, okay, and then minus, when I plug in 1, I get 1 times natural log of 1 minus 1. So plug in E, let's see, E, natural log of E is 1. So this is E minus E. So that thing is 0. And then what's natural log of 1? No?
0?
0. So that's 0 take away 1. So we're going to have minus -1, so that's +1. So this winds up being +1. So all we get is 0 plus 1 here, which is 1. So the last component of this vector function, or the vector, is 1. So I mean, this is just a straightforward problem in the sense of all you have to do is integration, 3 integrations, but each integration could be something different, right? The first one was basic, the second one was a U sub, and the third one was an integration by parts. Questions? So you might wonder, like, well, what's the use of that, right? Because the derivative gives you the derivative of a vector function can be viewed as velocity and then acceleration, right? But what about the antiderivative? Like, what is the use of taking the antiderivative of a function? We know in Cal 2, the antiderivative of a function would give you the area under the curve, right? Something like that. Do y'all see how that's not as easy to do here? Like, just think about a curve in 3-dimensional space, right? When you talk about area underneath a curve in 3-dimensional space, how do you talk about area? That's weird, right? Like, in 2-dimensional space, you just draw the curve and you just drop everything down the x-axis and talk about the area. But in 3D, it's a little more problematic.
So
Okay, so we'll address that, just not right now.
the volume.
Yeah, it could have something to do with volume, right? Yeah, we're just going to have to see where this goes. But right now, we don't have an immediate result of this. Like, we don't have an immediate geometric result of what the antiderivative represents. Okay? Now, we're going to start the next section. And when we do the next section, oh, wait, no, we're not starting the next section. Damn it. Let's see. I want to see how long. I'm looking at the clock here. Okay, so look, we'll do this one. Okay, so here we go. Suppose that I tell you that the derivative of some vector function is t e to the t and t e to the t and then t e to the t. That's the derivative of some vector function. And I tell you that the original vector function r evaluated at 0 gives you the vector 1, 1, 1. Then I want us to find what the vector function r of t is. All right, so let's see if we can't work through this and understand what's going on. Would you all agree that if I wanted to know what r of t was, since that's the derivative, I need the antiderivative of that? It should be the antiderivative of this, right? So let's find the antiderivative of this. All right, the antiderivative of that, well, some of these are going to be easy. All right, so the antiderivative of t is going to be 1/2 t squared. Power rule, right? The antiderivative of e to the t is itself. Now, what about the antiderivative of t e to the t? Not so easy. Antiderivative of t e to the t dt. I would need integration by parts. I would let u be t. I'd let dv be e to the t dt. I would differentiate down, du is dt. I would integrate up. I know I'm going through this fast, but that's because you took Cal 2 already. So I don't want to spend a bunch of time on this. I'm just showing you what I'm doing rather than just telling you what the answer should be. So I'm doing this, and now I'm doing ultraviolet minus the integral of voodoo. And so my final result will be t e to the t minus e to the t plus a constant. Oops. Hold on, sorry about that. Okay. All right, so we have that, and then t e to the t minus e to the t. Now, there's something missing here. Do you agree that for each of these antiderivatives, I had plus a constant, plus a constant, plus a constant? How do we do that here? I could put plus c in here and then plus, well, I shouldn't use c again because I used it here. So here's what I'm going to do instead of plus c. I'm going to do plus, and then out here, I'm just going to do like C1, C2, C3. These are all constants. So C1 is the constant that goes with that one. C2 is the one that goes with that one. C3 is the one that goes with that one. That makes sense? If I added these two vectors together, then they would appear here, here, and here. So that is my general antiderivative. But I'm also given that when you plug 0 in, you should get the vector 1, 1, 1, right? So if I take 0 and plug it into this, what would I get if I plug 0 into this? So it needs to be equal to 1, right? But that means, that implies, sorry, not 1. When I plug in 0, I'll put here, but, comma, r of 0 should equal 1, 1, 1, which implies, let's plug in 0. So if I plug in 0 here, I just get 0. And then e to the 0 is 1. And then I'm plugging in 0 here, that's gone. And then minus e to the 0, so that's minus 1. Plus our constants, which we don't know. That should equal the vector function 1, 1, 1. Okay, so saying that when we plug 0 in, we get this vector, means that when we plug 0 into this for t, it better spit out 1, 1, 1. So all you need to figure out now is what are these constants? So what does C1 have to be?
1.
1, because when you add it to this, you better get 1, right? So we're doing it's a little equation we're doing. We're doing 0 plus C1 has to be 1. So it has to match up with that. And then the other equation we're doing is that 1 plus C2 has to be 1. So that's this 1 plus that C2 has to be 1. And then we have the last one, -1 plus C3 has to be 1. And just solve each of those for C. For C1, 2, and 3. So we should get C1 is 1. C2 is what?
0,
0, and C3 is
2.
2.
2. Okay, so that allows us to put together our final answer, because we were asked what is R of t? Well, R of t needs to be 1/2 t squared e to the t, e to the t minus e to the t, and then plus the vector 1, 0, 2. Again, you did that in Cal 2. They would give you like a second derivative, and then you'd have to work backwards to build up to the original function. And they had to give you what were called initial conditions. And that's exactly what this is. This is like an initial condition or a condition. Doesn't have to be an initial condition, but in this case, it's called an initial condition because we're starting at t equals 0. So that would mean like the start of time. Any questions there?
Yeah. Would you be able, instead of having 2 vector plus a vector, can't you just like
Combine.
already add it? Yeah.
Yeah. Like you could just put like +1 here and then nothing there. And then over here on this one, go +2 and just get rid of it.
Yeah.
Yeah, absolutely. Yeah, those would both be correct, however you wanted to do it. Okay, so this is an application. I said I'd tell you one application. If we know A of t is the acceleration function of a particle moving in space, then the first antiderivative of the acceleration gives you velocity, and then the antiderivative of velocity would give you position. So you can work backwards. If you have acceleration, you work backwards to position. Okay. I don't know, how many of y'all were shown this in Cal 2? So let me put this up here first. How many of you who've taken physics have seen this formula before? Something like that.
Yeah.
Yeah. So what is that? Do you know what that is? What that formula is for?
It's position function.
Yeah, this is the equation you're given in physics that tells you if you take an object, let's say you have a cliff, let's say you drop a ball or something off this cliff, then this tells you how high the ball is off the ground after a certain amount of time if you're on Earth, okay? And this only works on Earth, and you have to take air resistance out of the equation. If you want to add air resistance, it becomes more complicated, but that's the formula that you're provided in physics class. So the things here are T is time, and it's measured in seconds. And then D0 is your starting height, and that's measured in feet. And then V0 is your starting velocity, and that's in feet per second. So that V0, D0 is just a number. It's how high the rock is off the ground. V0 is a constant. That tells you, like, are you just letting the ball go, or are you going to throw the ball up in the air first, or are you actually going to throw the ball down, right? If you throw the ball up a little, it's going to take longer for it to go up and then back down. If you throw the ball down, it's going to get to the ground faster. So this V0 is letting you know how fast the ball is moving when it leaves your hand, okay? And then nothing else, you don't have to provide anything else. So the only things you have to plug in are these two things, and it'll tell you where that object is on Earth, right? Okay, that's a position function. So I don't know if you were shown this in Cal 2 or not, but if you look at acceleration, okay, when you let a ball go, right, or a rock or whatever it is, what is the only force acting on that rock?
Gravity.
Gravity. Okay, so what is the acceleration of gravity?
9.8.
9.8.
In this case, it'd be, I think, what, 32 feet per second.
Yeah, so the acceleration of gravity is 9.8 meters per second per second. And it would be negative because we usually say negative is down, right? So what we know is that for any object on Earth, the acceleration function for any object on Earth is negative 9.8 meters per second per second. But I'm going to write it in feet per second instead of meters per second. So it's negative 32 feet per second. That's a rough estimate here. Hold on, 9.8 oops, I know you can't see this yet. Okay, move this so you can see it. 9.8 meters converts to about 32 feet. Okay, so if we're going to say acceleration of gravity is negative 9.8 meters per second, that's about 32 feet per second. All right, that's the acceleration for any object that's just falling on Earth. Now find the velocity function. So what do you have to do? Take the antiderivative, right? So we'll take the antiderivative. The antiderivative of the negative 32 is negative 32t, right? Right, okay, plus some constant that I don't know. I'm just going to call it c, all right? Now that's our velocity. Now what's our position function? I'll call it d of t. Well, the antiderivative of that should be the antiderivative of negative 32t, which should give me what, negative 16t squared, right? And then plus c, antiderivative of a constant is constant times the variable ct, and then plus some other constant, which I'll call d. And this is this formula. See, now c is the starting velocity, and you can see that because if I go to velocity and I plug in 0, what am I going to be left with? If I plug 0 in here for t, all you're left with is c, right? So this c will always represent your starting velocity. And then d, well, if I plug 0 into this, 0 here and 0 here, d is the starting height, right? And so there it is. And so what I'm saying is that this works on any planet. If you know the acceleration of gravity on that planet, you can always recover the position function by just integrating twice. Further, it will always be a quadratic function, right? It should always be quadratic because you're starting with a constant as your acceleration. Interesting, right? Okay, I went off topic there a little bit, sorry. All right, this is just saying that, look, if we have an acceleration function where it's a vector function, then going backwards gives you velocity, going backwards again gives you position. All right, I'm not going to do this one. I'll just talk you through it. You start out with the acceleration function, you go backwards once, and you'll have the velocity function plus a constant, and then you use this initial condition to get that constant. Once you have that, you integrate that a second time, and then use this information about the position to recover the constant on the position function. All right, so it's kind of like two iterations of what we did here. All right, that's it for that. All right, let's move on. So we're now going to talk about arc length and curvature. Arc length and curvature. So let's see how many of you remember this, or if you don't remember it, at least, well, hopefully you remember seeing this. I'm not sure if it was ever derived for you, but back in Cal 2, you were told that if you're given a function, we'll call this y equals f of x, and you cut it off, you start it here at A, and you end it here at B, that if you wanted to find the arc length, that meant if you wanted to take this curve, take it off the paper and stretch it out and measure its length, that there was a formula for it. And the formula was this: length equals integral from A to B, square root of 1 plus the derivative of the function squared dx. Okay, just a quick little show of hands for those of you who have your video on. How many of you remember seeing that formula at some point? Yeah? Okay. So I'm not sure if you were ever shown where it comes from. So I'm just going to show you quickly where it comes from. The idea here is that if you zoom in on one little piece of this, okay, you're going to have, so we're zoomed in on that. We see the little curve here. We're trying to approximate just that one little piece. Just how long is that little piece? So what we do is we imagine connecting the two endpoints with a straight line. And we say that that black line, however long that is an approximation to that blue curve. We're going to have some error. But what we'll do is we'll cut this into infinitely many little pieces like this. And so the error will get smaller and smaller and smaller. And that requires us doing a limit. And that's what the integral is all about. The integral is basically us taking a sum of an infinite number of things. Okay, so we just take this picture and we say, all right, well, how long is this piece right here? Well, that's the change in x, right? Which we call dx. Like when you take the limit, the infinitesimal change in x is called dx. And then this height right here is called dy. That's your infinitesimal change in y. And so by Pythagorean, this little l should be dx squared plus dy squared. Does that make sense just mathematically, just geometrically? Yeah? Okay, so the next thing I'm going to do is I'm going to go up here. Remember, y is a function of x, right? So if I take y is equal to f of x, and I take the derivative on the left side with respect to x, then I get the derivative of f, right? That's what it means, right? The derivative of this would be the derivative with respect to x, which is what f prime is. That's the definition. And now what I'm going to do is I'm going to solve this for dy by multiplying both sides by dx. And so what I have now is an expression for dy that I can stick right here. So the length of that little piece should be dx squared plus f prime of x. Oh shit, I forgot the square root, didn't I? Sorry. I forgot Pythagorean, this should have been L squared, shouldn't it? L squared equals this. Okay, so I meant to take the square root. I forgot to. Right, this squared plus this squared equals this squared. So if I want to know what L is, I need to take the square root of those two. Okay, now do you see that these both have a dx squared in them? since they both have a dx squared, I can just do this. Factor a dx squared out of both. If I factor it out of this one, I just have a 1. If I factor out of this one, I just have a f prime of x, but that's still being squared, right? And then I can take the dx out of the root as a single dx. And that is that formula right there, right? That's what that is. So you're just saying, hey, L, which is the length of the whole curve, is just the infinite sum. That's what that integral represents. It's an infinite sum of all of these little pieces. And we're going to start at A and end at B, where A is the left endpoint and B is the right endpoint. Okay? That's what it was in Cal 2. Now, we are interested in knowing what the formula is if we're in Cal 3 and it's a vector curve, right? A curve through 3-dimensional space. Well, it's going to be the same exact principle, all right? The principle is just we have a curve, okay? But the only difference is when we estimate this, you have to imagine this is in 3-dimensional space, but I'm only going to show it in 2D. You'd still do a construction like this, but the difference is instead of this being dx and dy, this right here, well, I need to write this. If r of t is the vector function f of t, g of t, okay, then this length right here is how much f is changing by, right? And so this is going to be like f, this is going to be like the derivative of, how do I want to write this? I'll do it this way. Let's say that's x and this is y. So this is dx and this is dy. So if I want to know this little length right here, it's going to be the square root of the derivative of this guy right here. Okay, the derivative of this, which would wind up being f prime of t dt squared. Y'all see where I got that? I'll do it on just this one. If x is equal to f of t, sorry, f of t, then if I take the derivative of x with respect to t, I get f prime of t. And so I just multiply both sides by dt and I get an expression for dx. And that's this expression. And then I have the same expression for g, but it'll be g prime of t dt squared. And then they both have a dt being squared, so I can pull that out. Make sense? Okay, that's all I wanted to show you. I'm going to get to the formula. Here it is. So if you're given a 2-dimensional vector curve and you want to know the length of the curve, it's going to be equal to this right here. Okay, it's equal to this. It's the derivative of the f function squared plus a derivative of the y function or component function squared. But notice that, and this is the really cool thing, is that this whole thing, by definition, is just the magnitude of the derivative. And think about what's the derivative of this? Well, the derivative of that is a new vector function, f prime of t, g prime of t. And then if I ask you for its magnitude, you're just going to take the square root of each of those things squared and add it together, right? Which is this. So we have a very, very, very nice formula for this. The formula is that the length of that curve is going to be just the magnitude of the derivative. You just have to integrate that, integrate the magnitude of the derivative in your business. That's pretty cool. Now, if we go to 3-dimensional space, it's the same exact formula. Okay, now you have 3 component functions, but still, if you want to know the length of the curve, you're just going to take the integral from a to b. Now, a and b are the limits on t here, right? So you're just going to take the magnitude of the derivative and then integrate that function. That's it. So we have really nice condensed formulas for this. Let's do this. Can somebody tell me what we're about to prove? In this question, what are we about to prove?
The circumference of a circle.
if we, whatever did we get for an answer here should be the circumference of a circle, the unit circle, right? Because that vector function draws the unit circle, right? If we go from 0 to 2 pi, it should draw the unit circle. And so our answer should be pi r squared, right? But r is 1, isn't it? Because the radius here, right? The radius here is 1. So our answer should just be pi. Let's verify. All right, so here we go. We know that the length of this should be the integral from 0 to 2 pi of the magnitude of the derivative, right? The magnitude of the derivative. Let's go ahead and do that. The derivative, let's put that over here. We've done this already today. Negative sine t, cosine t, right? And now the magnitude of that, so the magnitude of that vector is just the square root of each of the components squared. Could it be that easy? Could this be that easy? Right? Let's see, that's the square root of, the negative doesn't matter on the sign, does it? Because it's going to get squared. Sine squared t plus cosine squared t, it's 1, right? So that's just the square root of 1, which is 1. So we're integrating 1 with respect to t. And that will be equal to, well, the antiderivative of 1 is t. We're evaluating that from t equals 0 to t equals 2 pi. Right? What are we going to get here? Did I say pi r squared? I did say pi r squared earlier, didn't I? Just ignore that. I was thinking area of circle. I don't know why. I said that. I did say that was a mistake. Our answer, remember, we knew coming into this class that the area, circumference, I said it again, circumference of a circle is 2 pi r, right? That's what the circumference should be. And in this case, the radius is 1. And so our answer should be 2 pi. So when we plug in 2 pi, we get 2 pi. When we plug in 0, we get 0, we get 2 pi. All right, done. Now, just out of curiosity, what would have happened if I would have, instead of doing r cosine t, instead of 1, what if I just put an r in there and an r in here, just an arbitrary fixed constant r? How would that have changed things? Let's see, my derivative here would still be r, negative r sine t, and then r cosine t. Because they're constants, you just tack them onto the front. And then when you do your squaring here, you're just going to have an r squared here, r squared, which you can factor out. And so what you wind up getting is just an r here. I'll let you do the math on that. You just wind up getting that. You do square root of r squared. So you just get r here. So that would make this turn into the integral from 0 to 2 pi of r dt. And the antiderivative of r is rt. And rt, yeah. And then you're going to go from 0 to 2 pi. And now when you plug in 2 pi, you get 2 pi r. And when you plug in 0, you get 0. So your general formula is 2 pi r. So I'm not sure in Cal 2 if your professor showed you, like, verified that formula or not. I know I do it in my class, but it's a little harder in Cal 2 because we wind up, I believe, having to use trigonometric substitution to do the integral. Because we're not working with a vector function in Cal 2. We're working with a straight up function, and so it's a little more complicated. It's really easy work here to do. All right. Is that wrong for me to say that was easy work? I mean, that was pretty straightforward integration, like properties of sine and cosine, pretty straightforward. Okay, so we just verified that. Now, how about this? So I don't know if you remember that picture. This was that circle, but it's 3-dimensional. So it's circle, and then the z component was growing. So it was this springy looking thing. So we're drawing this, right? We're drawing it, and we're actually going to stop somewhere. We're going to stop. We're going to have like one full revolution. So it's going to draw a circle if you look at it from the top, but it's actually a spring. And so we want to know the length of that thing, right? That's what we want to know. Can you see how this could have some applications? I mean, being able to find lengths of things in three-dimensional space. All right, so here we go. We want to find the arc length of this curve from the point 1, 0, 0 to -1, 0 pi. Now notice we did not specify the restrictions on t, did we? They aren't specified here. But how could we get them? Right, we need to figure out what is t between here.
Could it be 0 and 2 pi?
0, okay, so I agree 0.
I think it's just 0 to pi because the z value just goes from 0 to pi.
Yeah, look at this last component, it's t, right? So if we're supposed to start with our last component at 0, that means t would have to start at 0. And then we have to stop when we get to there, so that would have to be our pi. Now let's just confirm it. If we start at 0, what would r of 0 be? Let's just check it. What would r of 0 be? We plug in 0 here, here, and here. Cosine of 0 is 1. Sine of 0 is 0. And then, of course, 0 is just 0. That would be the vector function. That corresponds to that point, right? And then let's just check our pi. Cosine of pi is -1. Sine of pi is 0. And then, of course, we just replace t with pi, we get pi. And that corresponds to that point. So it looks like we're going to go between 0 and pi. All right, so we know the restriction. So we know that the length of this is going to be the integral from 0 to pi. But now we need to take the derivative and then take the magnitude. So the derivative of that vector function is a new vector function, negative sine t, cosine t, and then what? We have one additional piece, right?
Just 1.
1. And now we need its magnitude. So it's a square root of, let's see, sine squared t. I'm going to square them because the negatives won't matter. Cosine squared t. And then, isn't that just 1? Okay. What does that turn into?
Square root of 2.
Root 2. Okay, so this is just, it's a constant, right? Root 2. Well, we got lucky here. Square root of 2 is all we're integrating. And so the antiderivative of that is going to be root 2 t evaluated from t equals 0 to t equals pi. So I plug in pi, I get root 2 pi, and I plug in 0, I get 0. Again, I mean, I don't think that we can understate how easy that very difficult problem just was, right? You know, if we would have started today out saying, hey, you know, remember that curve? Remember that thing? How long is it? You would probably think that the math on that was going to be pretty complicated, but it actually turned out to be really, really simple. Let's look at this one though. All right, so I give you the interval, right? 0 to 1. So you already know the limits of integration, but we need a derivative and then we need a magnitude. So here we go. The derivative of this. All right, so let's see. We take derivative of that first one. The 3/2 comes down and the 2's cancel. So I get 3t to the half. And then here, derivative of cosine of 2t. I'm going to get -2 sine 2t. -2 sine 2t. Anyone have a question on that? Chain rule there. Derivative of sine 2t would be 2 cosine 2t. And now the magnitude. square root of. All right, here we go. Squaring each of the components. 9t, okay, that's not bad. Plus, let's see, when I square that, I should get 4 sine squared 2t. And then the next one should be plus 4 cosine squared 2t. Right, that's what would happen if I square each of those. Look at these. These are nice, right? I can factor 4 out of those. If I factor a 4 out, then I would just have 4, and then I would have the sine squared 2t plus cosine squared 2t, which becomes a 1, right? So this is just going to give me a 4 here. So we have square root of 9t plus 4. Unfortunately, we can't do anything with that. That is what it is. So we're going to be doing the length will be equal to the integral from 0 to 1, and then it'll be square root of 9t plus 4 dt. And if I were the one doing that integration, I'd probably do a basic U substitution, just a basic U sub. But what I'm going to do instead is I'm going to just go to Wolfram alpha, and I'm going to integrate square root of 9t plus 4 on 0, 1. See if it does this. All right, so here's the exact answer. The approximate is about 2.8794. All right, so that curve is about 2.8, 2.9 feet or inches or miles or whatever it is that you're measuring in. Any questions? By the way, here's the curve we just did. That's what it looks like in 3-dimensional space. All right, now we're going to move on to, let's see, time-wise, we're good. Okay. So now we're going to move to a new concept. Now this concept is the concept that we do not have in Cal 2 or Cal 1. Okay, so this is something new in terms of a definition. It's this thing called curvature. And it's something that we can calculate. It's a number that we calculate. If we're given a curve, 3-dimensional or 2-dimensional curve moving through space, right? It's a number that represents how quickly a curve's direction is changing at a given point. So it's like, you know, how rapidly how big is your curvature, right? Think about a car coming around a turn, right? So it's a measurement of that curvature. Now there are 2 formulas for it, all right? The first formula is this one, which is, you know, just pay attention to what this is. Remember what capital T is? Capital T is the unit tangent vector. So you have to go back to what we did earlier in this section, or in the previous section. Capital T is the, well, let's just look at it, okay, just so you know. It's the magnitude, almost there. There it is. Okay, so capital T is the derivative of the vector function divided by its own magnitude. That's what the capital T is. But the formula for curvature is that you have to take the derivative of that. See that little prime mark? You have to take the derivative of that capital T and then take its magnitude. And then divide that by the derivative of the vector function's magnitude. And that will give you a number. And that is what is that we define the curvature to be that number. Now you will also get the same answer if you do this formula instead, which is a crazy formula. It's the first derivative of the vector function cross product with the second derivative. You get, remember when you do cross products, you get a vector. So that'll give you a vector, then you take its magnitude. And then you divide it by the magnitude of the first derivative cubed. All right, now I'm not gonna go through the derivation of these formulas. You're just gonna have to take those on faith. But those give you the same answer, so you have the choice. I do say here that this one's only good in R3, but there are ways to go from two-dimensional space to three-dimensional space. So we can still do it in 2D, but this one, of course, because of cross products are really only useful in three-dimensional space. So, all right, so here's an example. This is that nice circle, right? We've been doing this enough. I have the computer calculating the curvature. Do y'all see that it's not changing? Okay, and that's because circles have constant curvatures. It makes sense. You got your steering wheel turned and you're just same turn the whole way, right? That's constant curvature. As opposed to something like this, where let me go back. In the beginning of this, you've got really tight turns, and then you start to not have to turn your wheel as much, I guess, if you're driving a car here, right? So look in the beginning, look how big the curvature is. See, my curvature is calculated to be about 10, but as I move along, notice that the curvature is getting smaller, okay? So we are just trying to calculate those numbers. So let's go back to this. Let's show that this is constant. Let's show that the circle has a constant curvature. So I'm going to need a couple of things here. I mean, geometrically, it makes sense that it should be constant because it's a circle, but we have to show it. So I'm going to try it with the first formula. The first formula was that K is equal to the magnitude of capital T prime of T over the magnitude of R prime of T. All right, that's the first one I'm going to try. So first, let's get capital T of T. Capital T of T, by definition, is R prime of T over its length. Right? Okay, so we've done the derivative of this so many times. The derivative of this is just going to be negative sine T cosine T. We're going to divide that by, what is its length? What's the magnitude of this derivative? Should be 1, right? When we take this, square it, add them together, square root, we'll get Pythagorean identity, sine squared plus cosine squared. So we should get 1 here. So capital T is this. Okay, now we need to take its derivative. So what's the derivative of this? Well, that's going to be negative cosine T, negative sine T, right? And then we need the length of that. But same thing, Pythagorean, this will just give us 1, right? So I know that the numerator of this is 1 over, now the denominator was the derivative of R of T, which was up here, is this one, right? And it was its length, which is actually this, which we already know is 1. So the bottom is 1 also. And so the answer is 1. So we have a constant curvature of 1. Right? T does not have an impact at all on that answer. Yes.
So if it wasn't a constant curvature, would it be an equation instead of a number?
It would be a function of T. So our answer would have T in it so that it would depend on where you were on the curve, and that would somehow dictate the curvature. We're going to do an example right now where the curvature is not constant. So look at this one. So that example right there, okay, this curve does not have constant curvature. Here is the vector function that draws it. Is that right? Hold on. Was this 3D? No, this is not 3D. No, that's just an example. Okay, this is just an example, but this is a three-dimensional vector function that does not have a constant curvature. Does not, all right? So let's find the curvature of this one. All right, so a lot of things. Do y'all want to do the second formula on this one? Or let's try the first one. Let's try the first one. There's a couple of things we're going to need. Every single time we do this, we're going to need to know what the derivative is, right? Let's find the derivative. The derivative of this is just going to be 1, 1, 2t, right? Derivative of that. I'm gonna need its magnitude. Okay, so that I'm gonna need a couple of times here. So take the magnitude of that. The magnitude of that is the square root of 1 squared plus 1 squared plus 2t squared is 4t squared. There, right? Okay, and then what I need to do to find capital T of t is I need to take this derivative and divide it by its own length, right? This divided by its own length, which means we have this 1 over that value, then 1 over that value again. Because remember, the 4t squared plus 2, square root of 4t squared plus 2 is just a constant, and I'm scaling by that, I'm dividing through. So then I have 2t over, shit, man, 4t squared plus 2. Ugh. That's just capital T, right? Remember what I need. Go back to the curvature formulas. I need capital T's derivative and then its magnitude. So y'all ready for the derivative of this? Oh man.
The other one looks so much easier.
Yeah, this is starting to be really bad because if I want to take derivative of this, I'm either going to have to use quotient rule or chain rule. I would probably rewrite that as 4t squared plus 2 to the negative 1/2. That's the way I'd rewrite that. And then I'd start using chain rule. So then it would become derivative would be negative 1/2 4t squared plus 2 to the negative 3/2 times the derivative of what's inside, which is 8t. That would be the derivative of just that first piece. And then I'd have another piece here. This one would be quotient rule. I could do chain rule product, but do y'all see this is getting very bad very quickly? And then even after you finish this, then you have to take the magnitude. So then you're gonna have like the square root of all of that squared plus all of that one squared plus all of that one. Oh man. And that's just the top. So maybe we should try the other one. Maybe the other one's better. So the other formula was, whoa, how did I get there? The other formula was, I need the first derivative and cross it with the second derivative. Okay, so let me do that. First derivative crossed with second. So I'm going to first derivative. I think I'm just gonna, there's my first derivative. I'll just change colors. Here's my first derivative. Okay, I need the second derivative. Second derivative of this. Oh man, that's a really nice one. 0, 0, 2, right? I need to cross those. So I'm gonna move all this out of my way because it's just in my way. I don't want to erase it because I want everyone to see that at this point I said, no, stop, right? No more of this. Okay, so I need to cross those. So if I do r prime of t crossed with r double prime of t, then I'm doing that thing where I do I, j, k. I put one of the vectors here, 1, 1, 2t. And I'm crossing it with 0, 0, 2. And then that's where I play that game and I'm going to get an answer here, a vector. Right? So I cover up the i's and I do my little determinant here. So I should just get 2 there. Cover up the j's. I should get 2 there again, but then it's going to be negative. And I cover up the k and I should just get 0. Okay, go back to the formula. What do we need? We need the r prime crossed with the r double prime. We got that, right? We have that vector. We need its magnitude. So let me go get its magnitude. So this is equal to that. So the magnitude of that should be equal to the square root of 4 plus 4 plus 0. That's root 8. Well, I like that. And then we need the magnitude. The formula said on the bottom, we need to be dividing by the magnitude of the first derivative cubed. The magnitude of the first derivative cubed. I have a little more room here. So let me write this down. The curvature should be equal to the magnitude of r prime t crossed with r double prime t, which I already know, over the magnitude of r prime of t cubed. Okay, the top was the square root of 8. Now what about the bottom? It's the square root of something cubed, right? So I'm taking r prime of t and I'm taking its magnitude. So I'm taking the square root of each of the components squared, and here's a derivative. So it's this squared plus this squared plus this squared, which we had done right. Well, it's down here, right? Here it is. It was just this, right? Yeah. So this is just going to be 4t squared plus 2. There it is. There's your curvature. Now notice that the curvature depends on t, right? You have to give me a t, and then I will tell you the curvature. So at 0, right? If t is 0, the curvature would be, let's see, square root of 8 over, see if that's 0 here, then this is going to be the square root of 2 cubed. Right? That's a number. But as t gets bigger, right, what happens when t gets, I don't know, goes to, let's say 100? Well, it's going to give you a number, right? But it'll be a much smaller number because t getting bigger means the denominator gets bigger and the numerator stays fixed. So your denominator starts growing, the whole thing starts going to 0. So as time goes on, your curvature is approaching 0, which would mean straight line is where you're headed. Like in a limit, if you went to infinity, it would be approaching a straight line. Does that make sense? All right, let's see what else we got. All right, that's it. Wow. All right, so for the homework, there's a couple of problems here. Let me check that. Let me cross-reference that with the homework that I have assigned here. Yeah, it's exactly the same. Okay, good. So it says the same thing here. All right, so we were able to get through 10.8, which is good. So next time we'll start the next section, functions of several variables. Actually, this is a new chapter. We're starting a new chapter now. So we're going to put all the vector stuff away for a while, and we will bring it back when we need it. But you'll see that we're going to use it a little bit here and there, but it won't really come back like full strength until we get to chapter 13. So chapters 11 and 12, let me verify something, hold on. Yeah, so chapter 11 has to do with partial derivatives. That's what chapter 11 is called. And then chapter 12 is multiple integrals. So we'll do, you know, there will be little vector stuff in there, but chapter 13 is called vector calculus. So we have now laid the framework. We have all the tools in the toolbox that we need. And now we can go and start doing other things. All right, everyone. If you have any questions, I'll hang out for a few minutes. I haven't posted anything for a new mini exam yet because we're behind, so I need to figure out how I'm going to do this.
Yes, sir. Thank you.
All right. Have a good one.